So I'm talking about intro to binary exploitation. This is like somewhat of a difficult topic, so I wanted to give a talk over it so uh, people could have like some expectations of how to do things. Um, Binary exploitation really isn't taught in any class. You kind of just figure it out by yourself. So let's go ahead and get started. So first of all, I wanted to make this talk like not require computer architecture as like a prerequisite. So I'm gonna go over like the important parts of computer architecture before talking about actual binary exploitation. So we'll start with that. Um, so what is computer architecture in the first place? This is the definition that I pulled off of Wikipedia. Uh, Kind of looks like a bunch of garbage. I don't really care about that. So I simplified it to just assembly and circuits. Uh, and because most of us are CS majors, we don't care about the circuits part. So we're just going to talk about assembly. Um, so yeah, uh, there's a few like vocabulary words that I'm going to use. And here's like a list of them. So assembly is just like an overall term for like low level human readable code. You'll see why I say human readable in a second. Um, but assembly is not like a specific language, it's like a class of languages, I guess. Uh, and an ISA, instruction set architecture, is like the specific language in the class of assembly, I guess. Um, and then so machine code is specifically low-level machine readable code. So we'll see that like assembly is like a representation that is readable to a human, and machine code is that same instruction but encoded as like a number so a computer can read it. And then the two big important things that you need to get off the slide is a register is like tiny storage on the CPU that stores integer data, and then memory is like a big storage in RAM that stores like almost everything else. So here's like a list of common ISAs. You don't really need to care about this, but x86 64 or AMD 64 is like the most common ISA. This is what your computer runs. This is what most computers run. ARM 64 is probably what your phone runs. Your router might also run this. Your router might actually run MIPS 64. x86 is like old computers, and ARM 32 is like uh, old phones. And then people in the chat are saying, "Where's RISC V?" RISC V is not really on devices yet, so I didn't put it on here. But it's another ISA. There's a huge list of these. This is just like 5 of the more common ones. There's like probably 100. I don't know. So how do we like describe programs in terms of assembly? So like our programs usually consist of like doing stuff like running some instructions, like doing a for each loop or something like that, a for loop, I don't know. And then having stuff which is just having variables like a state that you can use to do computations. So without both of these, you can't really do interesting computations. So in assembly, we would say doing stuff is executing assembly instructions, and having stuff is using like the memory and registers for variables. So starting off with what registers look like, they store like strictly numbers, right? Each register can store an 8-byte number. There's only like 16 registers on the CPU. Like quite a few of them have special purposes. So we actually only have like, I don't know, 12 maybe registers that we can use for program data. So there's not a whole lot of room to store variables in registers. Um, we need to use something else in order to store like large data structures or strings or anything else. But the registers are essentially used for like holding variables before making computations. Um, so if I was going to do like 5 + 8, I would put 5 in a register, I'd put 8 in a register, I would add them, put the result in a different register, uh, and something like that. But if I needed to like do a computation on a string, I couldn't use a register. I would have to do something else, which I'll talk about in a second. Yeah, there's two other bullet points on the slide, which is like where to find variables and what instructions to run next. Uh, we'll talk about this in a minute. Some of the registers are like important metadata for your program, and we will talk about which registers those are and what metadata they hold. So the other thing that I was talking about is memory. So memory can just be thought of as like a huge array of bytes, right? Um, and then if you've heard anybody ever talk about what a like a pointer or like a memory address or something like that, those are just indexes into this big array. This is a giant array. It's like I don't even know how big, 2 to the 64 size. Like it's huge. Um, and all of our important program data is stored here. So like global variables are stored here. The actual program code is stored here. Uh, all of the like variables for functions are stored here. Everything is stored in memory. And you can see I've like kind of labeled where things go. So globals are like at the front of memory. Um, the like code is at the after the globals, and then the like function variables and stuff live on the stack all the way at the top of memory. So yeah, memory stores like 99% of your variables. The actual code for the binary is stored in memory. Um, and then these are these like special registers I was talking about: RIP, RBP, and RSP. So RIP actually points to what instruction is going to be executed next. So essentially, like when your program is executing, it needs to know uh, like where in the program it's currently executing, and RIP is this like instruction or this register, and then RBP and RSP keep track of memory on the stack. We'll talk more about the stack in a second. Um, so as I said, function variables and writable data live on the stack, and the stack like grows and shrinks its size while the program runs. So, and I guess it's also worth noting that the stack grows towards uh, smaller variable or smaller addresses, which is somewhat confusing. So the stack starts at the very highest address in the memory space, and when it grows towards 0. Um, so uh, yeah, I think I have more slides on the stack later on, but yeah. So as far as machine code goes, this is what I'm talking about when uh, we have instructions in the like code encoded into memory. So uh, memory is all just like byte numbers, right? So we encode assembly instructions as numbers, and then we just stick them in memory and let the CPU deal with it. So here's an example like assembly instruction. So move EAX 0x dead beef. So this would move uh, the value 0x dead beef into the register EAX. Um, so you can see like the machine code is somewhat human readable. You at least see that it's doing a move. And then, or sorry, the assembly is at least somewhat human readable. You see that it's doing a move. And then the machine code is like the actual number representation of uh, the assembly. So the machine code is what would be in memory, and assembly is like a shorthand for the machine code. Um, so uh, it might also be worth noting that architectures are a little Indian. So the integer deadbeef is encoded kind of backwards. You can see like EF is the first or the byte at index 1, and then BE, and then AD and DE. That isn't super important, but it might be confusing for you if you've never seen it before. So just be aware of that fact. Um, Now we're going to talk about like some actual assembly instructions and like what they do. So the first one we're going to talk about is the move instruction. This is like probably the most basic instruction you can think of. It literally just loads a value into a register. So this one would load the value 0x deadbeef into EAX. Um, the push instruction is another important instruction that we need to know. So this just pushes something onto the stack. So it's going to decrement RSP, which is like the stack pointer, by 8, and then store the value in RAX into the memory address at RSP. So it's if you want to think about this like intuitively, it's just going to put the value of RAX on the top of the stack and increment the size of the stack by 8. And then the pop instruction just does the opposite. It takes the value off of the top of the stack and puts it into RAX, and then decreases the size of the stack by 8. And then the next one is call. So this is what you would use if you're calling a function. So if we were to say like call square, where like square is a function that just computes like x squared, I guess. It jumps to the address for square, and then it pushes the current instruction pointer onto the stack, and then it jumps to the call address. This is a fairly important instruction. I would say if you need to know any of the instructions, it is this one and ret. So ret just pops the value off of the stack and puts it into RIP. So you can think of ret as just like a pop RIP. It's essentially the same thing. Yeah. So ret would be what's at the end of a function in order to like continue the previous function. Would it push the current RIP or the next RIP? It would push the current RIP. So this is saving the saving where you are in the current function, calling square, and then when square returns, it's going to go back to where you left off in the current function. So now we're going to talk about functions. So this is where I said we're going to talk more about the stack in a minute. This is actually like solidifying what I was saying about the stack. So functions are almost completely self-contained in what's called stack frames. So essentially the like variables for the current function and some amount of extra function metadata is stored in a stack frame, and these stack frames are like per function call. So this is what a stack frame would look like. So you can see we have like the variables for this function called foo. So it has all of the variables, and it has a saved RBP and then a return address above that. So the registers RSP and RBP keep track of where the current like stack frame end and beginning are. So like this is what it would look like for some arbitrary function. Yeah, and then if we had like multiple functions that are like calling each other, like you would have in like a real program, you would see something like this, where foo gets called and then foo calls bar, right? So essentially foo is going to yeah, so foo is going to have its own stack frame, and then bar is also going to have its own stack frame. And you can see that like uh, these things have listed where they point. So like the return address for bar would be pointing toward into foo, where bar was called, and like the saved RBP in bar points to where the RBP was for foo. Um, yeah. Hopefully this slide makes sense. This slide, like this picture right here, is a very important thing to have in your mind if you're going to do binary exploitation. Um, so stack frames, like the size of these stack frames are like variable. So they may change based on what function you are calling. And the like stack frame size is defined at the beginning of a function. So if we look at this example for like multiplying two variables, right, we can see right here that we call sub RSP16. So this is growing the stack frame size by 16, and then doing like the just doing the computation. So for this one, the stack frame would have size 16. Um, yeah. Uh, okay. So now for calling convention. So calling convention is essentially just like a convention agreed upon um, by the compiler that will pass arguments in a certain order. So um, essentially, it only really means that the first argument to a function will be passed through the register RDI. The second one will be passed through RSI. The third one RDX, and so on. Just in these like arbitrary register order. Um, and then seventh and onward arguments are passed through the stack. And when a function returns, the return value is put in RAX. So this is just like an arbitrary convention that exists for like no real reason. I don't know. Worth keeping in mind though. Very fairly important if you're going to do anything using arguments or anything, uh, or you need to like look at return values for a function. Okay, so now for like actual exploitation, right? Um, how do we like use the fact that like computer architecture exists to our advantage, I guess. Um, so if you noticed, we never said anything about like checking uh, uh, like where addresses are or like where the return address goes or anything like that when we were talking about functions. So um, there's essentially like unprotected memory accesses that we can exploit in order to uh, do arbitrary things in our program. So we'll talk about that in a second, but first we'll just talk about like what situations will we like run into problems. So uh, anytime we use strings in C, right, we may run into problems. So uh, strings in C are just arrays of characters, and there's like no bounds checking when accessing arrays in C. So uh, we can like if the program is poorly written, we can read and write out of bounds of our array. So essentially, we can read and write into data that is not allocated to our array. So a very common function that this happens with is called getS, right? So getS, if you go like read the like C man page for it, which is like the manual page, uh, it says never use getS. It is impossible to tell without knowing the data in advance how many characters getS will read. So what getS does is it just reads a string from the user. So if the user types in a string that's way longer than the array size, then it's just going to like overwrite a ton of data that shouldn't be overwritten. And it says like gets has been used to break computer security, use fgets instead. So we'll go over an example of how we can use like gets to just completely break a program. So using the same example as before, we're just going to talk about this like 2-line function where we create a 50 byte string and we call gets on it. So if we look over here to the assembly generated, we see the stack frame size becomes 64. We load the address of RBP minus 64 into RAX. We move RAX into RDI. So RDI is now the address RBP minus 64. And then we call gets. So what this is essentially doing is just calling gets with the value RBP minus 64. So there's this string is 50 bytes long, so we can write 50 bytes in here in the stack frame for sure without overwriting anything. And then if you notice, there's an extra like 14 bytes that are just like unused in this example. And this is just because C typically tries to round things to like the nearest 16 bytes. So this 50 just got rounded to 64. So we could actually write 64 bytes in here without breaking anything. So this is what our stack frame actually looks like for this function. So we have x0 all the way up to x63, and then we have the saved RBP and then the return address. So how can we actually like get an exploit off of this? How do we actually like do anything interesting with this? What we're gonna do is write past the end of x and overwrite this return address. So if we are able to overwrite the return address, when user input calls this ret instruction, it's going to jump to this return address. So we can essentially tell the program to continue its execution anywhere we want. So when the function returns, it's going to jump to whatever address we write. So we will go from this state to this state, right? So we can essentially overwrite the return address with some other function, and it's going to call that function. So if we had a binary that has like a get flag function, which is somewhat common in like easier binary problems, we could just call get flag, and then we would get the flag. So it might be worth noting that you can also like overwrite further than this, and the functions will like essentially chain together. So if we overwrite with like the address to function 1, the address to function 2, and then the address to function 3, what's going to happen is our function is going to return, and then we'll jump to function 1. Function 1 is going to execute. When it returns, it's going to jump to function 2. And then when function 2 finishes executing, it's going to jump to function 3. And this is like commonly known as like a ROP chain, right? We'll talk more about this in a minute. But how do we actually like do anything interesting with like so like what do we want to overwrite RIP with, right? Easy problems have like a get flag function where we would just overwrite function 3 with or function 1 with get flag, right? But that's not super interesting. So like what real world program is going to have a get flag function in it, right? Probably none. So what can we do instead? So like built-in functions from the C standard library are often useful targets to run. So if system exists in the C standard library, we could call that. So what system does is it just executes a program, like an arbitrary program that we specify. So we could call system binsh, and we would get a shell. That would be useful. Uh, we could jump to a ROP gadget. So I'll talk about ROP gadgets on the next slide and what they do. They're less interesting than jumping to system, but uh, system will only exist in the binary if system is used by the binary. So if the binary source code never calls system, system won't exist. Um, we could also jump straight to system. So if the system address does not exist in our binary, like we can't find a deterministic address to system, we can leak some amount of data that will allow us to jump straight to system, or we could jump to a one gadget. These last two cases are a bit complicated, so I won't talk about them in this talk, but I might talk about them in a future talk. But okay, so you may be like now wondering like what the heck is a ROP gadget? Why did he just like put that on there and then not explain what they are at all? So I will do that now. A ROP gadget is just like a short instruction sequence followed by a Ret instruction. So uh, you can kind of think about this as like a really small function, right? Like a one instruction function. Um, they can be put in a ROP chain the same way that functions would be put in a ROP chain, and uh, they're useful for like getting control over registers, like single registers, because usually a function is going to do like a fairly large computation, and the registers are just going to be like in a completely wonky like state after the function is run. But using ROP gadgets, you can get like very precise control over exactly what is in each register. Uh, so pop gadgets are the most useful case of this. So like something where you have a pop RDI or like pop RSI or something like that, and then a ret. And I'll show you why on the next slide. But okay, so several questions in the chat. Ethan says, can ROP gadgets only contain a single instruction? No. So ROP gadgets can be like an arbitrary amount of instructions. You could think of a function as a really long ROP gadget. Uh, so a ROP gadget is essentially just any sequence of instructions followed by a ret. Um, the only like difference is that most sequences of instructions followed by a ret are like uninteresting in your binary. Um, so like if you had, I don't know, if you just had like an arbitrary instruction before a ret, it's probably not going to help your exploit at all. But if you see like a pop something and then a ret, that's fairly useful. Um, the longer a ROP gadget is, probably the less useful it's going to be. There's no way to call anything that exists outside of the program stack, right? Um, so we would be calling things that are in the like code segment. Here, I can scroll back like a ton of slides back to the very beginning. Uh, so uh, we would be overwriting the return address to go to things down here in the code, right? Um, we can't overwrite the if we were to overwrite the return address to something in the stack, we would try to like actually execute code on the stack, and that is like an invalid thing in most programs. There's a like a exploit mitigation called DEP or INX. So that mitigation essentially says the only code that can be executed as instructions lives in the code segment. Anything in like the stack or the globals cannot be executed as code. So we will be jumping around in here. Um, yeah. Okay. So what can we do with this, right? So we could use the pop gadget kind of like this. So we could call like pop RDI a value that we want to put in RDI and then system. So what this is going to do is it's going to call this this pop gadget, right? Um, and this is going to make the program jump to like a pop RDI instruction. So then the program is going to call pop RDI, which is going to pop this value off of the stack, and then it's going to do that ret instruction. So the ret instruction is going to make us jump to system. So um, this essentially like allows us to call system with like an attacker controlled argument. So we could pretty easily call like system binsh. Uh, can we can a ROP gadget just trivially be a ret? Yeah, so that's actually a somewhat useful instruction. So um, you may run into problems where uh, you like the program just crashes even though your like ROP chain looks fine. So what can happen is the program can check the like byte alignment of the stack, and if it's not 16 byte aligned, it will like crash the program. Um, so uh, to fix that, we would just call ret once, which is just going to like uh, increase the size of the stack or decrease the size of the stack to be like 16 byte aligned, and then you could call whatever function that checks the like stack alignment. That's not super like important to know, but sometimes it happens and it's annoying. And then finally, like ROP gadgets can be used finding a tool just called ROP gadget. There, you can find like the GitHub for that if you Google it. It just shows you how to do a ROP. It just like goes through the binary and finds all the ROP gadgets and like prints them out. It's pretty useful. Okay, so yeah, somebody just sent it in the chat. So now we'll do a demo. If you go to nugatory.ponables.org, you should see two binary problems there. I just pulled them off of like the last CTF. Um, and we will be doing these over the next like few minutes. Uh, yeah, probably. Let's stop the recording.